We'll start in 1 minute. Today we'll be starting section 7.4 on integrals of rational functions by partial fractions. So recall that a rational function has the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions. If the degree of p of x is less than the degree of q of x, then the rational function is called a proper rational function, and it can be expressed as a sum of simpler fractions. So for example, if we have f of x equals 3x squared plus x plus 5 over x to the third plus 2x squared plus x plus 2, we see that this is a proper rational function. The degree of the numerator is 2, the degree of the denominator is 3, so it's a proper rational function. And this rational function can be expressed as a sum of smaller fractions, 1 over x squared plus 1 plus 3 over x plus 2. So we'll verify that this equation is true. So if we begin with 1 over x squared plus 1 plus 3 over x plus 2, and if we write this as a single fraction or a single rational expression, we need to have a common denominator. In arithmetic or algebra, before you can add two fractions, you have to have a common denominator. So if we multiply the fraction on the left by 1 in the form x plus 2 divided by x plus 2, and multiply the fraction on the right by 1. This time the form 1 takes is x squared plus 1 over x squared plus 1. And now that the denominators are equal, we can add the fractions. So in the numerator, 1 times x plus 2 is x plus 2, plus 3 times the quantity x squared plus 1, which is 3x squared plus 3. And then the denominator, you can leave the denominator in factored form if you want, or you can multiply the two factors. Either way is okay. So we'll simplify the numerator and put the numerator in standard form, so we get 3x squared plus x plus 5, and then the denominator x to the third plus 2x squared plus x plus 2. Okay, so it looks like we have successfully verified that this proper rational function is the sum of two smaller fractions. So being able to do that will enable us to evaluate integrals of proper rational functions. So we're going to rewrite this integral as an integral of the sum of those two smaller fractions. So this indefinite integral is equal to the indefinite integral of 1 over x squared plus 1 plus 3 over x plus 2. And we know how to find the antiderivatives of those. So maybe by now you know what the antiderivative for 1 over x squared plus 1 is. If you don't remember, we can always find it by a trig substitution. We can use x equals tangent of theta. Or you just might remember that we've done it a fair number of times. The antiderivative for 1 over x squared plus 1 is 1 times the inverse tangent of x over 1, or just the inverse tangent of x. And then an antiderivative of 3 over x plus 2. Oh, what's that going to be? Yeah, plus 3 times the natural log of the absolute value of x plus 2. So if that didn't come to mind immediately, remember you can use the substitution rule. And then the idea here is if you have an antiderivative of du over u, that's equal to the natural log of the absolute value of u. Or you can just remember. Okay, so you might agree that finding the antiderivatives of the two smaller fractions is easier to take on than if you try to do the whole thing by itself. Okay, the next page. Okay, some rational functions are improper. So if f of x equals p of x over q of x is a rational function, and the degree of the numerator, the degree of p of x, is greater than or equal to the degree of the denominator q of x. Then what we want to do, we want to divide the numerator p of x by the denominator q of x using the division algorithm. And the result will be p of x over q of x equals s of x plus r of x over q of x. So the capital S of x is the quotient that results from dividing the numerator by the denominator. Capital R of x is the remainder, and q of x is the divisor because that's in the denominator. So the quotient capital S of x and the remainder R of x are just polynomials, and the degree of the remainder will be less than the degree of the quotient. Okay, so we'll have to review, or we should review, polynomial long division. And here we have an improper rational function, x to the third plus 8x squared plus 13x plus 7 divided by x plus 1. It's improper. And so before we integrate an improper rational function, we want to put it in a simpler form by long division. So for this part, we'll just verify that this equation is true. So we'll use polynomial long division. The divisor is x plus 1. And we're dividing it into the numerator, x to the third plus 8x to the second plus 13x plus 7. X will go into x to the third, x to the second times. So we put x to the second up in the quotient. And then we multiply x to the second times the divisor. X to the second times x is x to the third. So we put that in the x to the third column. And then x to the second times 1 is 1x squared. So we write plus x squared. Then we subtract. X to the third minus x to the third is 0. 8x to the second minus x to the second is 7x to the second. And then we start the cycle over again. X goes into 7x to the second plus 7x times, and we multiply 7x times the divisor. 7x times x is 7x squared. And then plus 7x times 1 is plus 7x. And then we subtract again. 7x squared minus 7x squared is 0. 13x minus 7x is 6x. And we have one more cycle left. X goes into 6x 6 times. So we put plus 6 in the quotient. And 6 times the divisor. 6 times x plus 1 is 6x plus 6. And then subtract again. 6x minus 6x is 0. 7 minus 6 is 1. Okay, so the quotient, x squared plus 7x plus 6, we see that up here. This is the quotient. The remainder is 1, and so 1 over the divisor, x plus 1, is where this comes from. Okay, so now that we've verified that this equation is true, we can evaluate this indefinite integral of the improper rational function. So we can write this as the indefinite integral of the quantity x squared plus 7x plus 6 plus 1 over x plus 1 dx. And this is a pretty simple integral to evaluate. We just get x to the third over 3 plus 7x to the second over 2 plus 6x plus the natural log of the absolute value of x plus 1. Pretty simple. Okay, we'll go on to the next level. So most of the time, we're going to have to do the hard work rather than just verifying that we have a partial fraction equation. Okay, so any proper rational function can be integrated by first rewriting, if necessary, the rational function as a sum of simpler fractions called partial fractions, whose antiderivatives we already know how to find. So we will have 4 cases to consider. So those 4 cases will be described. In all cases, we're going to assume that the rational function p of x over q of x is a proper rational function. So in other words, the degree of the p of x in the numerator will be less than the degree of q of x in the denominator. In case 1, the denominator q of x is a product of distinct linear factors. A linear factor in the variable x can be written in the form ax plus b, where a and b are real numbers and a is not equal to 0. So if the denominator is a product of distinct linear factors, then we can express it this way: q of x equals the first linear factor, a sub 1 x plus b sub 1, times the second linear factor, a sub 2 times x plus b sub 2, and so on. So if we have k distinct linear factors, the last one is a sub k times x plus b sub k, where no factor is repeated. Okay, then in the partial fraction decomposition, there will exist constants a sub 1, a sub 2, and so on up through a sub k, such that p of x over q of x is equal to the sum of these simpler rational expressions. Okay, so a sub 1 through a sub k are constants, and 0 is a constant. So sometimes you'll find that one or more of those constants is 0. So don't be surprised if that happens. Okay, so let's evaluate this indefinite integral of a proper rational function. The indefinite integral of 3x minus 2 divided by x squared plus 5x plus 6 dx. I think what I want to do, I'll write down the integrand on another piece of paper. So I'm using another piece of paper so I don't run out of room on this one. So we want to express this rational function as a sum of simpler rational expressions. So first we factor the denominator. This factors pretty nicely. The two factors are x plus 2 times x plus 3. And so this is case 1. The denominator has two distinct linear factors, two different ones. So according to what was stated on the previous page, this can be written as some constant a divided by x plus 2 plus b over x plus 3. On the previous page, if I followed the form that was on the previous page, I would have put a sub 1 in that numerator and a sub 2 in that one. But I just prefer to use different letters for the different constants. Okay, so the goal is to determine what the values of a and b are. So now what we do is we add these two fractions. So I'll write 3x minus 2 over x plus 2 times x plus 3. And then what we're going to do is, before we can add the two fractions, we have to have a common denominator. So I will multiply the fraction on the left, a over x plus 2, by 1 in the form x plus 3 over x plus 3. And then I will multiply the fraction on the right, b over x plus 3, by 1. This time the form 1 takes is x plus 2 over x plus 2. Okay, now that we have a common denominator, we can apply the arithmetic to the numerators. So here we have a times the quantity x plus 3. So we'll write that as a times x plus 3 times a. And then plus b times the quantity x plus 2. That's plus b times x plus 2b. So I'll rewrite the one on the left. So we're going to combine like terms. We have an a times x plus b times x. So we can write that as the quantity a plus b times x. So a plus b is the coefficient of x. And then the constant is plus 3a plus 2b. Okay, the goal is to determine the values of a and b. So what do you suppose we do next? Well, this numerator 3x minus 2 has to be equivalent to this numerator. The coefficient of x on the right is a plus b. So that coefficient a plus b must be equal to the coefficient of x on the left. So a plus b is equal to 3. And the constants must also be the same. The plus 3a plus 2b must be equivalent to negative 2. So we'll write 3a plus 2b equals negative 2. Now we have a system of two linear equations in two variables a and b. So this is something that you learned in intermediate algebra, how to solve a system of two linear equations. So there's a number of ways to do it. We can solve it by substitution, or we can solve it using the addition method. I think what I'll do is apply the addition method. I'm going to multiply both sides of the top equation by -2. So multiply both sides by -2. So I'll get -2a minus 2b equals -6. And I'll leave the bottom equation the same. 3a plus 2b equals -2. And then we can add equations. So when we add the equations on the left-hand side, the -2b plus 2b is 0. -2a plus 3a is a. And on the right-hand side, -6 plus -2 is -8. Okay, so the value of a is -8. And then we can use any one of those equations to determine what b is. I'll use this top equation, a plus b equals 3, and replace a with -8. So -8 plus b equals 3. Add 8 to both sides, we get b equals 11. Okay, so to summarize, I'll write down the summary here. So 3x minus 2 over x squared plus 5x plus 6 is equal to -8 over x plus 2 plus 11 over x plus 3. Okay, we'll transfer this over on the other page. So here's the original page. So we found that 3x minus 2 over x squared plus 5x plus 6 is -8 over x plus 2 plus 11 over x plus 3. So now we can pretty easily evaluate this indefinite integral. So we might as well go ahead and do it. So this is the indefinite integral of -8 over x plus 2 plus 11 over x plus 3 dx. And we get -8 times the natural log of the absolute value of x plus 2 plus 11 times the natural log of x plus 3, the absolute value of x plus 3, plus the constant. Okay, that wasn't so bad. Now we'll go on to case 2. So in case 2, the denominator q of x is a product of linear factors, some of which are repeated. Okay, so suppose the linear factor ax plus b is repeated m times in the factorization of the denominator q of x. So the partial fraction decomposition will have to include powers of that linear factor up to the power m. So the first one, a sub 1 over ax plus b. Then the second one, a sub 2 over the quantity ax plus b to the second, and so on and so on and so on. Since the linear factor appears m times altogether, the final partial fraction will be a sub n over the quantity ax plus b to the power n. Okay, so here's an indefinite integral. This is proper because the degree of the numerator is 2, and what's the degree of the denominator? It's 3. Yeah, we have two linear factors. X plus 1 squared is x plus 1 times x plus 1, and then times x minus 2. So the denominator has a degree 3. So it is proper. And this time, we write 2x squared plus 3x plus 4 over x plus 1 squared times x minus 2. And so our partial fraction decomposition, the factor x plus 1 appears twice. That's what x plus 1 quantity squared means. So one of the partial fractions will have the form a over x plus 1. The next one will be b over x plus 1 squared. And then we still have this linear factor, so we write c over x minus 2. Okay, so once again, I'll use a different piece of paper to do all of the computations on this one. The goal is to find the values of a, b, and c. Okay, so we're going to add the three fractions on the right-hand side, the three rational expressions. So we have to have a common denominator. So the left-hand side, 2x squared plus 3x plus 4 over x plus 1 squared times x minus 2. So we start by multiplying a over x plus 1 by 1. So what form will 1 take? Well, the least common denominator is x plus 1 squared times x minus 2. So the form 1 takes will be x plus 1 times x minus 2 over x plus 1 times x minus 2. Okay, then we multiply b over the quantity x plus 1 squared by 1. What form will 1 take this time? Well, x plus 1 squared, we have those two factors. We just need the factor x minus 2. So the form 1 takes this time is x minus 2 over x minus 2. And then multiply c over x minus 2 by 1. And the form that 1 takes this time is x plus 1 squared divided by x plus 1 squared. Okay, so we'll multiply all of those numerators and combine like terms, and then we'll write down equations involving the coefficients and the constant. So first, in this numerator, let's multiply the two linear factors. X plus 1 times x minus 2 is x squared minus x minus 2. And this one is easier. B times the quantity x minus 2 is just b times x minus 2b. And then plus c times x plus 1 quantity squared is x squared plus 2x plus 1. So this is all over the single denominator, x plus 1 squared times x minus 2. Okay, let's distribute multiplication by a in this product, and then also distribute multiplication by c. So we'll get ax squared minus ax minus 2a, and then plus bx minus 2b, and then plus cx squared plus 2cx plus c. This is all over x plus 1 squared times x minus 2. Okay, then we can start collecting like terms, but I'll rewrite the rational expression on the left, 2x squared plus 3x plus 4 over x plus 1 squared times x minus 2. Okay, so let's identify the x squared terms. We have ax squared plus cx squared. And we can write that as a plus c, the quantity a plus c times x squared. And now the x terms. We have minus ax plus bx plus 2cx. So I'll write this as plus the quantity, negative a plus b plus 2c times x. And then the constant of the minus 2a minus 2b plus c is the constant minus 2a minus 2b plus c. And now we can start writing equations involving the coefficients and the constant. On the right-hand side, the coefficient of x squared is a plus c. On the left-hand side, the coefficient of x squared is 2. So that means a plus c equals 2. Then the coefficients of x. On the left-hand side, the coefficient of x is 3. On the right-hand side, negative a plus b plus 2c. So negative a plus b plus 2c equals 3. And then the constant 4 is equal to negative 2a minus 2b plus c equals 4. So is there hope that we can find A, B, and C? Do you remember a rule of thumb for solving systems of linear equations? A system of linear equations can have any number of equations and any number of variables. So in general, if you have n distinct variables and n equations involving those variables that are independent, then you can solve the system. So we have 3 variables and 3 equations. So we're assured that we can solve the system as long as the 3 equations are not multiples of another equation. They have to be independent. But these are clearly independent. So what we do next, so I suppose, since this equation on the left involves just 2 variables, I'll solve for one of those. So how about if I solve for A? A equals 2 minus C. And then in each of the other 2 equations, we'll replace A with 2 minus C. So negative A, that's the negative of the quantity 2 minus C, and then plus B plus 2C equals 3. On the right-hand side, replace A with 2 minus C, so we get negative 2 times the quantity 2 minus C, and then minus 2B plus C equals 4. When we get finished simplifying these 2 equations, we'll just have 2 equations in the variables B and C, so we can solve that system of 2 linear equations. But we have a little bit of algebra and arithmetic first. So negative 2 plus C plus B plus 2C equals 3. The equation on the right. Get it so everyone can see it. Okay, then negative 2 times the quantity 2 minus C is negative 4 plus 2C minus 2B plus C equals 4. Over here, combine like terms. C plus 2C is 3C plus B. And let's go ahead and add 2 to both sides, so we get 5 on the right-hand side. And here, combine like terms. 2C plus C is 3C minus 2B. We'll add 4 to both sides, and we get 8. Okay, this time I'm going to multiply this equation on both sides by 2. Multiply by 2. And I'll put the result below this one. So multiply both sides by 2, we get 6C plus 2B equals 10. Add those equations, we get 9C equals 18. And that means that C is equal to 2. Okay, so if C equals 2, remember our equation for A. A is equal to 2 minus C, so A is equal to 2 minus 2, or 0. And then the only number left is B. So replace C with 2. 3 times 2 is 6. 6 plus B is 5. So B is -1. Okay, I'll write down the summary down here, and then we'll transcribe it to the other page here in a second. So we have 2x squared plus 3x plus 4 over x plus 1 squared times x minus 2. So we found a to be 0. I'll go ahead and write it here. 0 over x plus 1. B is -1, so I'll write minus 1 over x plus 1 squared. And C is 2, so we get plus 2 over x minus 2. Okay, now on the other page, okay, so this is 0. A is 0. What's B again? -1, and C is 2. Okay, so we can write this integral of -1 over x plus 1 squared plus 2 over x minus 2 dx. Okay, so that seems like a lot of work, but the payoff is good. These are pretty simple integrals to evaluate. So what's the antiderivative of -1 over x plus 1 quantity squared? At first glance, it might seem a little tricky, but if you think of the substitution rule, then it's not so bad. So let's write them separately. Okay, substitution rule. So if we assign u to be x plus 1, then du is dx. And then we just have -1 over u to the second du for the integrand. You can take it a step further. You can write it as -1 times u to the -2 du. And then we get -1 times u to the -2 plus 1 divided by -2 plus 1. So -2 plus 1 is -1. -1 divided by -1 is +1. And u to the -1 is the same as 1 over u. Sorry, I'm off the screen. Okay, so this first one then is just 1 over x plus 1. And the other one, we know how to do that one. So this one is 2 times the natural log of the absolute value of x minus 2. Okay, so up here on this line, I'll just write what this is equal to. We found that we get 1 over x plus 1 plus 2 times the natural log of x minus 2 plus a constant. Okay, let's get started on case 3. We won't get too far, but we'll at least get introduced to it. For case 3, the denominator q of x has irreducible quadratic factors, none of which are repeated. An irreducible quadratic factor has the form ax squared plus bx plus c, where a does not equal 0 and b to the second minus 4ac is less than 0. Okay, the zeros of an irreducible quadratic factor are non-real complex numbers. So let's remind ourselves how to find the zeros of a quadratic expression. Find the zeros of x squared plus 4x plus 10. So all we do is, to find the answer, solve the equation x squared plus 4x plus 10 equals 0. The solutions are called the zeros. So we can always use the quadratic formula. In this case, a is 1, b is 4, and c is 10. So we get x equals negative b, or negative 4, plus and minus the square root of b squared minus 4 times a times c, divided by 2 times a, so we get negative 4 plus and minus the square root of 16 minus 40 is negative 24, all divided by 2. We're about out of time. We could simplify this further, but you can see that the two solutions are non-real complex numbers. Okay, so on Friday, we'll continue this. Let's go ahead and take attendance. So online sign in, first name followed by last initial. Okay, Joshua. Here. What a part. Freshman Budlin. Daily Coffee. Jason Kohler. Sarah Nicholas. Audrey Mills. Nicholas. Okay, I've got everyone. See you on Friday.